And now let's work problem 670, which is this frame. Got a couple of features I wanted to make sure and point out. And I've done more free body diagrams than you might need to do. Some things are sort of inherently obvious, but the problem is they're inherently obvious for a statics problem, but they're not always true for a dynamics problem. So if you're not careful, statics can get you into some bad habits when you go into dynamics. And one, for example, is in statics, you've got this weight hanging here. Weight's your M times G, and I think we had 75 kilograms. The tension equals the weight. But that's because the A is 0. It's because there's a 0 over here. If this thing's accelerating, then the tension doesn't equal the weight. In fact, that's why it accelerates. But anyway, so it's a good habit to once in a while draw that again and remind yourself that 0 is what matters. So we get the tension, I call that the tension, and we get that equal to weight. And then the pulley, we've done this before, but just worth doing again. The pulley is supported by a pin, so the two forces on the pin, and then the two forces of the rope. Because of the moment is 0, then that's going to imply that the torques caused by the two forces are equal. If there's a moment of inertia, remember I times alpha, torque equals I times alpha. So if there's an I moment of inertia of the pulley and alpha is not 0, then that won't be true. But in this case, it is true. So really, I could have drawn that. You could have started off that way and just made those both T, and then sum the forces in the XY pulley, and you realize the two support forces have to be the same. Now, the other thing is that member AB, even though it's shaped as a rectangle, is a two-force member, so the force has to lie along that connects them. Because, I mean, you could draw it up and show AY and BY are equal to AX, or opposite and equal, and AX and BX are opposite and equal. But that means that your magnitudes of A and B are equal. I also use that to define my angles. You have to go back and look, but you'll see the opposite of beta is 1.5 and the adjacent's 2. So then I'm ready to draw the free body diagram of that member BC, which has the pulley on the end of it. I had called that O. You could quickly go and just draw your tensions there. You know, if you've done a lot of problems, you would do that, but that's because all of this is true. So I went ahead and left it. And now you got to be consistent. So since I drew OY and OX this way, then I have to draw both of them opposite on this picture. And so there's my response, CY and CX. There's my two-force member, B. Remember, A and B are equal. So I take the moments about C to get rid of these two. The only thing I don't know is B. So I've got the vertical part, B sine, times 2. We're doing it about C, so that would be counterclockwise. It's positive. The horizontal part will go through C, no moment arm. And then the O, the only part's the vertical part, OY, and that would be clockwise, so it's negative, and it is we're doing it about C, so it's 2.5. So if you can solve that for B, remember A is the numerically equal to B. And then we do the forces at X to get CX, OX, and the part of B that's horizontal. And then we do the moments about B in order to find CY. And so we have CX, CY, we've got A and B, and we've got the force at the pulley here. So to check that, I went ahead and used this diagram and added the forces in the Y. They did add to 0. And I went back to the entire frame and did a free body diagram, did the forces in the X and Y there to get 0. And I also took a moment about O that had basically everything I had calculated in it. So get all those to add to 0, and you're pretty confident you have the right thing. So that's a good one. Not too hard, but lots of good things to go back and review in it. If you have any questions, shoot me an email.